I guess you're all dying to hear about scalars from all of the discussions. Okay. So what's a scalar? It's a tensor of order 0, in this context at least. It's independent of the coordinate system. You all know this from before. I mean, if you change the coordinate system, the air pressure is the same, for example. And it represents a magnitude. And I don't think we have a lot more to say about scalars because you're also familiar with them. But vectors, there's some points there I would like to discuss a bit more. First of all, it's an order 1 tensor, which is a way of thinking about a vector which you might not have encountered before. Also, it has a magnitude and a direction. The magnitude is the same as the length of the vector. And here you see, because of that direction, they start looking different in different coordinate systems, even if they represent the same physical quantity. Let's see. I'll draw a figure to illustrate this. If I have a vector v in coordinate system unprimed, it's going to look different when I change to the primed coordinate system, but the vector is of course still going to be the same. We'll get back to the details. This figure illustrates that. Now if you start off by considering an orthogonal coordinate system, I will call it K, and it's going to have 3 axes, x1, x2, x3. You'll notice that I don't use x, y, z anymore because I want to use the summation convention, so that's why I use the numbering scheme. Okay. The components of the vector v now in the K system are the following. Let's see, v1 is the dot product between the vector and the unit vector along x1. And equivalently, v2 and v3 are the dot products with the vector v and the other unit vectors. Meaning that the vector v can be written in the following way. It's v1 You'll notice I put a small subscript here. So it's vector with components v1, v2, v3 with respect to coordinate system k. Because if I change the coordinate system, the values of these vector components are going to change, even if the physical quantity doesn't. You've all seen this before, of course, but just to clarify things. Now if I go to coordinate system k prime, what is it going to look like? Well, then v is going to look like now if you go to k prime, Now we're in K prime, what does the vector look like? I can just do the same thing and denote it by there you go. So I can also write this equivalently as component I of vector v is going to be the I component of, well, it's the ith unit vector, in fact, times the dotted with the vector itself. Okay? Now I can relate the coordinate system K and K prime through a so-called coordinate transformation. And this coordinate transformation, in very general terms, looks like the following. First of all, it's some transformation coefficient times the first component in the not primed system. And similarly for the other two components in the system without the prime, in system K. And equivalently for all of these components in the prime system. Let's see. Now that's a lot of writing, so I will write this on the matrix form to show you something you're familiar with. Let's see, I can write it as x vector prime, that is the vector x in coordinate system K prime, is related to the vector x in the coordinate system K through a matrix multiplication. And A11, A12, and so on, those are the elements in the matrix A. And yeah, let's see. And also these elements are independent of the position, right? If I make the same, if I make one rotation, then I do it everywhere. So. So wherever I am in the coordinate system, the rotation looks the same. Okay. More generally than a matrix multiplication, or more simply perhaps, I can write this as xi prime aij xj. I wrote now all the information stored here, except I wrote it in a very small and compact fashion. And here, of course, I use the Einstein summation convention as always. And taking the derivative of this one, I can now figure out what's the aij. And the result is the following. So I get the constant, which doesn't affect the derivative. I take the derivative of xj with respect to some other x, xk. And this is aij, and well, this one is of course delta jk. the derivative of y with respect to x is of course 0. So it's only the diagonal terms where j is equal to k that contributes. And equivalently, the sum over j, only j equals to k contributes. So I found a formula for a ik, or if I now just change the name, it's aij again, if I change the letter here. And then I can write the transform as, in the equivalently, as xi prime equal to dx. All right, now you notice the summation over j's. And this is, of course, just aij. So there you go. To determine the aij's, you just take the derivative of all the x's in the one coordinate system with respect to the x's in the other coordinate system. Okay, any questions? So this is how we relate the vectors in one coordinate system to the other. And vectors need to transform in this way. Okay, and the standard sort of prototype vector, which you've all seen before, is the position vector. And what does the R vector do? Well, it just points at a point in space. So the vector R just points at a point P in space, and we can write it in terms of its component as x1, the first component, times x1 hat, the unit vector in the x1 direction, and so on for the others. Or in the summation convention, just xi, x hat I. Right. Now, to define what is really a vector, we use the following definition in this context. And that is that the three numbers v1, v2, v3, the components of v, those are the components of a vector if they transform like the components of the position vector. This is useful because, let's say, if I'm interested in the momentum vector, I can't really picture it in space like I can the position vector, because, well, I'm not sitting in a space that's defined by momenta. I'm sitting in a space defined by position, so it's easier for me to think about positions. But other vectors should behave in an equivalent fashion in their respective vector spaces. Okay, so we note that the vector v or vectors in general, are defined by their transformation properties. How do they transform? An example is that if I rotate my coordinate system, the magnitude of a force, for example, should not change. And this is something you've all seen before. Let's say the velocity of your car shouldn't be any different if you rotate the coordinate system. It will just point in a different coordinate direction in your coordinate system, but it's the physics is the same, so to speak. Okay, and because of this, I can write in the following fashion that Vi prime is Aij Bj. And now the Aij's are given with the same formula, right? I use the same formula as the position vectors. You'll notice that the factor Aij is the same no matter what kind of vector I'm transforming. Any questions? Yep, perfect. Any other mistakes or questions? Okay. Now we're going to discuss the various products that you can form using two vectors. And we can form several of these, and most familiar to you is probably the scalar product. The result of a scalar product is that you take two vectors, you form the scalar product, and you have a scalar afterwards. This is sometimes called a contraction because I start out with two rank 1 or order 1 tensors, and I end up with a order 0 tensor, which is a scalar. And it's pretty simple. I just sum the products of the components, or you can write it in matrix form. The scalar product is also called the inner product or the dot product. Okay. Now the second type of products is the vector product, which you also heard about before. It's also called the cross product. And we write this in the most compact fashion by looking at one of the components. In this case, epsilon is again the Levi-Civita symbol. It's not the dielectric constant, so this is just the permutation symbol or Levi-Civita symbol, which relates the components of A and B to the component of the cross product. And we went through this before, so I won't talk much about it. But this is actually an example of an order 3 tensor. So now you already see that tensors are very useful. The third type of product, which you might not have heard about, is the tensor product or outer product. Yeah, and the result from the vector product was another vector. So we have two vectors, a rank 1 tensor, and we get out another vector or another rank 1 tensor. In this case, we put in two rank 1 tensors or vectors, and we get out a rank 2 tensor. I use rank and order a bit interchangeably here, but let's see, order. I'll call it an ordered two tensor. Okay. And we denote this in the following fashion. A circle with a cross in it. And more compactly, we can just write it as the product of the components. AI, Bj. Now you'll notice that these are different, so it's not a summation anymore, right? Let's see. And I'll need some more space to clarify what exactly is the tensor product. Okay, now what is the tensor product? If I want to write it out more explicitly, I can just rewrite, first of all, the A and the B as their components. So it's A1 times the first unit vector, and so on. And the tensor product with the B written in similar fashion. I guess you have enough of an imagination to see what the rest looks like. And now I can just do this term by term. So I get A1, B1, and then X1 hat, tensor product X1 hat. And the next contribution is going to be A1 and B2. And the tensor product between the unit vectors 1 and 2. And I'm not going to write out all of this, but of course it has 9 terms, meaning it's giving me a rank 2 tensor, or order 2 tensor. And I can rewrite this in the form of matrices. It's the product between the A vector and the transpose of the B vector. So it's, well, if you recall the scalar product, you can write it like this. So it's similar except the other way around. And now this looks like the following: A1, A2, A3. Like this. So now I just get this row times this column. Well, that's just these two numbers. So I get A1, B1, A1, B2, A1, B3, A3, B3, A2, B1, A3, B1. The rest you can figure out for your own. on your own. So they form a matrix. And this will show you what these guys mean. So x1 hat, tensor product, x2 hat. No, well, why not? So that's the column vector times the row vector. So it's 1, 0, 0, 0, 1, 0. And we get a matrix with just one of the elements being equal to 1, and all the others are equal to 0. And that should be the A1, B2, so it's this one. So what this x1 tensor product, x2, and all the other friends of that guy does is to put the product of AI and BJ in the right place in the matrix, so to speak. So x1, x2 puts it up here. That's where that component should affect the resulting rank 2 tensor. Okay, any more questions about vectors or any of this? So we move on to the order 2 tensors. Which is basically the stuff that you haven't seen before in any calculations. And this is also defined by its transformation properties. And the rank 2 tensor, it transforms in the following fashion, which is completely analogous to the vector case. The tensor T, with respect to the prime coordinate system, is related to the vector, the tensor T in the not prime coordinate system by the transformation coefficients, which are there you go. The derivative of xy prime with respect to xk times d xj prime dxl. So now if you want, you can write this as a rank 4 tensor, in fact, or order 4 tensor. Aijkl. So it's a party of indices here, and half the alphabet is invited. So this is how you relate the tensor in one coordinate system to the same tensor in a different coordinate system. It's completely analogous to the vector case, and this is how you define the tensors and the vectors. Okay, and yeah, and actually Tij is the components of the tensor. So the nice thing about working with components is, of course, that components are just numbers, which means that they commute. So if I write this as a matrix, for example, matrices do not commute. So then I have to be careful about the ordering, and generally it takes more space to write and so on. So it's nice to work with the index form of when working with tensors. And in the same fashion as we write an arrow above the vectors, we sometimes write tensors by a double arrow. This is now an order 2 tensor because of the double arrow. And as we saw here, it's formed by the components Tij. So let's write that as Ti. It's a T11. First of all, the first component, upper left, let's say. and the first and second components in the first and second indices. And, well, this is stupid to write out this every time. So we use the summation convention again. So I multiply each component with a corresponding pair or tensor product between pairs of unit vectors in the directions I and j. This is pretty dry stuff, but we'll need this soon, so bear with me. And we often write this as a matrix. That looks like the following: T11, T12, T1. Oh, you can fill in the blanks yourself. So it's basically just a 3x3 matrix when you write it out like this. Except it can't be just any components in here, and they have to transform in the way that we specified here. And now that we know a bit more about tensors, I'm going to show you some properties of the tensor product, which we'll need. Let's see. First of all, if I have the tensor product between two vectors, let's call them u and v for the moment, and I want to take the dot product with this and a vector w. You can do this by looking at the indices, for example, right? And then I will find that I can contract this to a somewhat simpler formula, which is this part is a scalar now, of course, because it's the dot product. So the tensor product uv dotted with the vector w is actually pointing along the vector u, and multiplied the magnitude of u by this scalar product. And similarly, there's another rule. If I change the order, okay, and we'll need this in a moment. All right, it's a lot of indices, as you can see. If there are any questions, just feel free to interrupt at any time, because if we drop some of the indices, it's just going to become a total mess. All right. Now if I decide to write the tensor T as the tensor product of two vectors, which I could always do, I'm now going to be capable of trying to figure out what is the dot product between a tensor and a scalar, which we will need when we get to the physics. So what's this? And I can write this out now, because I can just write T as U tensor product V. First of all, it's equal to U. I just insert for T, and I take the dot product with the vector W. And that should be then just W dot U. No, I'm in the wrong place. Let's see. U V dot W. So it points along the U vector. And the magnitude is given by, well, the following. And equivalently, or also we can write, if you take the dot product in the other way around, if I take the dot product with a vector and the tensor like this, again I expand T as U tensor product V. And again I use the trick from way over there, and we get that this product points in the direction of V. And these two results are examples of what we call contractions, because I start out with a rank 2 tensor and a rank 1 tensor, and I end up with just a rank 1 tensor. Contraction is just then basically that we have some sort of loss of indices on the tensors. So we wanted to do this in index form, so let's go back to that. Then I can write T as the components Tij and the tensor products between the unit vectors and the vector V as just the components of V times the unit vectors in the coordinate system we're working with, because we're always referring to vectors and tensors with respect to some coordinate system, right? Okay, I'm sorry that I stare at my paper a lot, but there's so many indices here. So now, if I want to know what is W if it's equal to T dot V, now then I just expand T and V like this, and I start using the summation convention to try to well, gather terms and so on. Let's just see what it turns out to be. Sorry. So I just insert for T and V. The components are just numbers, so I'll extract those and, well, just multiply those together. And I'm left with xi times xj dot xk. And now I can use one of the tricks over there to make this a dot product, which makes this let's see, xi xj dot xk. And now as I have the dot product between unit vectors, I know that the result is just a Kronecker delta. And in the end, we end up with there you go. So a contraction is just the same as summing over one of the indices so that the index disappears. So this is the components of W, which was the result of a scalar product between a rank 2 tensor and a rank 1 tensor, or a vector, if you like. So I'll just write this as using the summation convention as always. Yeah, and often you can just drop the cross product here. Because there's not really any other way of interpreting xi, xj. Okay, and yeah, and this is the outer product, not the inner product. So there's no dot product here. These indices are not the same, so it's not the dot product. They might look a bit the same, but it's not, because the result is a rank 2 tensor. Yeah, and comment on the naming. A rank 2 tensor is sometimes called a dyad. Okay, and we also have in general higher order tensors. And they basically behave like the tensors you've already seen in the following fashion. As always, defined by their transformation properties. So I have any number of indices on this tensor, separate, as you see that dot, dot, dot here. And then I simply relate this to some tensor T, L, M, several others, and then finally N by taking the partial derivatives. Let's see. Let's see. L, M, N. Finally, times T, L, M, N. Okay, so it generalizes by just putting more of these partial derivatives in between up to the order you need. And they transform by the partial derivatives of the position coordinates. So it's just a straightforward generalization of the order 1 and order 2 tensors. And as an example, on a higher order tensor, we saw the Levi-Civita symbol. Which is also sometimes called the Levi-Civita tensor. And well, it's an example of a rank 3 or order 3 tensor because it has 3 indices attached to it. And we have time for some questions, I believe. Oh, it can't all be perfectly clear. Come on. I'm almost as confused as you from all the indices, so.
The properties of the tensor product, they simply defined that way, or?
Well, if you want to figure it out, as we've seen, we work by indices, right? So it's UI, W, let's see, UI, Vj, right? The let's see, UI, Vj, that's this part, right? And then it's W, let's see, W,
That's the WJ.
Wj, right? And now it's just a summation of these, and that's the scalar product.
Yeah, but that's because, well, that's how you define it just now, but is it just defined that way, and that's why this is?
Well, if you define the tensors by the, let's say, the indices, like this, and use the summation convention, this is what you get out. And you can show it by explicitly writing these as x1, x2, right?
Yeah, but I had to make a choice and say that W had to be WJ when I did the final configuration. Because I don't really know anything about the U plus V.
So you're asking if they commute?
Well, no.
If I move it over?
They don't commute. That's
Yeah.
How do you know that it's supposed to be WJ, not WI?
Ah, right.
Or WK for that matter. So is that just a definition?
I don't have any immediate answer to that. I'll try to think of that until the next lecture, okay? And see if I have a good answer. It's not simply defined that way, but, well, you can write it as matrices. That's the safest, I guess. You can write it as matrices, and those don't commute. So if I write it as U1, B1, a 3 by 3 matrix, and then I have the components of W, then it's clear, right?
Yeah, okay. That's because it's with that given if U and B and W aren't really, well, ordinary vectors.
Yeah. So if I change I to J, I essentially transpose it and move it on this side. Okay. So was that a satisfactory answer? Okay. Was there another? I thought there was another hand somewhere. Okay. If there's no more questions, then I'll see you on Wednesday.